In this video, we're going to start going through Lewis dot structures or electron dot structures, two names for the same thing. And I'm going to be using this handout in this video. I do have this posted on Canvas for you. So it might be a good idea if you have a printer and wanted to just hit pause, go print this handout, and then come back because I'm going to be taking notes right on this. If you don't have a handout, that's fine. Or if you don't have a printer, that's fine. You can just, take notes as you normally would in paper or on your tablet. You're probably going to have to hit pause a couple times also just to keep up because I'm not going to rewrite it. I'm just going to read through it. So if you need to hit pause to make sure you get everything copied down, please do that. So Lewis dot structures or electron dot structures. I tend to use the word Lewis structures, but I do say electron dot structures on occasion. So just do know that those are two words for the same thing, or two names for the same thing. And what we're using electron dot structures for is to determine how the valence electrons in a particular molecule, so a compound with covalent bonds, are distributed throughout that molecule. This has nothing to do with the shape of our molecule. We're going to use Vesper theory for that, and we'll also do that this week. But this is just determining essentially what's bonded to what, right? If I was to look at the water molecule, is oxygen in the middle and it's bonded to hydrogen, or is it hydrogen bonded to oxygen? Just essentially how they are connected. Do I have lone pairs? Do I have double bonds? Do I have triple bonds? All we're doing with the Lewis structures is we're determining how those atoms are connected, and then do they have lone pairs or not? So how are the valence electrons distributed throughout that molecule? Electrons are going to be represented by dots. I do tend to use lines for bonds instead. A single bond is going to be 2 electrons, so 2 dots. And again, I like to use lines. So if I was to, in that water example, if I do this, this is actually represented as 2 dots because there's 2 electrons there. So a single bond is going to be 2 electrons, so 2 dots, or a line. And again, I'm going to use lines. 4 electrons, it would be a double bond, right? If a single is 2, a double is literally double that. So if I wanted to draw a double bond between 2 atoms, I could draw 4 dots. I am likely to draw 2 lines instead. So these would mean the same thing. These would mean the same thing. A triple bond is literally triple that of a single bond. So if a single is 2, a triple is 6. So 6 electrons are 6 dots. If I wanted to draw a triple bond, I can do those 3 lines. If I wanted to use dots instead, that would be my triple bond. Lone pairs are going to be 2 dots. Never draw a line for triple bonds. A line is only going to represent a bond, so no line. If you draw lines for if you draw lines for lone pairs, I am actually going to take off for that. I'm going to mark it incorrect. So up on this original oxygen I did, if I wanted to put a lone pair on it, I'm going to do it like that. If you were to draw your lone pair like this, you're actually going to lose credit for it because that's not the correct way to draw our Lewis structures. So we can have a single bond, which is a single line or 2 dots. A double bond, which is 2 lines or 4 dots. A triple bond, which is 3 lines or 6 dots. And then lone electron pairs, also called non-bonding pairs. And those are going to be represented by 2 dots. Don't draw any lines for your lone pairs. Before we get into the rules for drawing our Lewis dot structures, I do want to remind you on how we're determining the number of valence electrons, right? Because step number 1 is going to say determine the number of valence electrons. So let's just do a couple. If I was to look at hydrogen, right, and draw its electron configuration 1s1, we're just going to draw a couple here. If I was to look at carbon, 1s2, 2s2, 2p2, forgot the 2. And then let's look at chlorine. 1s2, 2s2, 2p6, 3s2, 3p5. So remember our valence shell, right, is our highest value for N. And then our valence electrons are the electrons in that shell. So if I look at hydrogen, I only have the first shell, right? There's only a 1, that's my highest value for N. So my valence shell is shell 1. If I look at carbon here, I have a 1 and then I have some 2s. Remember, my valence shell is my highest value for N. So my valence shell is going to be my second shell, so when N is equal to 2. And then when I look at chlorine, right, I have my first shell, my second shell, and then I also have my third shell. So my valence shell for chlorine is my third shell, so N equal to 3, right? Whatever your highest value of N is when you determine its electron configuration. And then the number of valence electrons is the number of electrons in that shell. So if we go back to hydrogen, in my first shell I have 1 electron, so it has 1 valence electron. If I look at carbon, remember we're not differentiating here between subshells. I'm not saying valence subshell, I'm saying valence shell. So everything in the second shell is going to count. So I have 2 here and another 2 here, so I have 4 valence electrons. For chlorine, again, it's everything in shell 3. So I have 2 in an S subshell, and I have 5 in a P subshell, but they're both in the third shell. So for this one, I'm going to have 7 valence electrons. And then our shortcut, right? If we look at the periodic table for the A groups, right? So for my main group metals, the ones that have the Roman numeral A, if we use that method, right, the AB method for naming them, the group number will tell us the number of valence electrons they have. So hydrogen is in group 1A, I have 1 valence electron. Carbon is in group 4A, I have 4 valence electrons. Chlorine is in group 7A, I have 7 valence electrons. Again, though, be really careful. Your periodic table is never your answer to a why question. If I was to ask you, why does chlorine have 7 valence electrons? It is not because it's in group 7, right? Chlorine does not consult the periodic table to figure out where its electron should go, right? The periodic table is just a tool. It's never going to be our answer. The reason it has 5, right? We would go through all of our quantum numbers and then we put electrons in them following Aufbau principle and Hund's rule and Pauli exclusion principle, and we would see that in the third shell I have 7 electrons. So again, the periodic table is just going to be my shortcut, but we're going to use it here because we don't want to have to draw the electron configuration out for every atom in our molecule. So for main group elements, right, the group number, if you're using that AB method, so the group number for the A block is going to tell us the number of valence electrons that it has. So that's going to be our shortcut. So our first step here, determine the number of valence electrons. We're going to look at the periodic table. We're going to look at the group number. If the molecule has a negative charge, right, if it's negative, remember it's gained electrons. Electrons have a negative charge, so if my molecule has a net negative, I have to add electrons to it. If the molecule has a positive charge, it's lost negative, right? It's lost an electron, so we're going to have to subtract an electron for it. So I'm going to go down to our examples here, and we're going to figure out the number of valence electrons for all of these examples. So you're going to want your periodic table handy because we're just going to use that shortcut. So my number of valence electrons is the first thing I want to do. So hydrogen is in group 1A. So I'm going to say 1 electron. There's 2 hydrogen, so that's going to give me 2. Oxygen is in group 6A. So I'm going to say 6 valence electrons. There's 1 of those. And then when I add that together, 8 electrons. When I draw my Lewis structure then for water, I need to have 8 dots. Or you remember, it's okay to use lines, you just want to count each line as 2 dots. So 8 line dots, however you want to do it, so it comes out to 8 electrons. Phosphorus, group 5A. Fluorine is in group 7A. I happen to have 3 fluorines in this molecule, So 3 times 7 is 21. 21 plus 5 gives me 26 electrons. So when we're done drawing this, I need 26 electrons. So dots, lines, however you want to do it, but you can't have less than 26. You can't have more than 26 if you want to be correct. Ammonium, NH4, it's one of the polyatomic ions that hopefully you know now. So how many valence electrons for nitrogen? Good, 5, right? We're just finding it on the periodic table. We're using that as our tool to remember how to do it. It's in group 5A. Hydrogen, 1 each. There's 4 of them. And then 4 plus 5 is 9. And then we don't want to forget this positive charge, right? It's pretty small there, but there is a positive charge. And then remember, if something has a positive charge, it's lost electrons, so I need to subtract 1. Be really careful with that. It's super tempting to see the plus and then add, right? But the whole reason it has a positive charge is because it's lost a negative charge. So just be careful. CO3 2-, what polyatomic ion is that? Hopefully you recognize it as carbonate. Carbon, group 4A. Oxygen, group 6A. There's 3 of them. So 6 times 3 is 18 electrons. 18 plus 4 is 22 electrons. And then carbonate does have a -2 charge. Remember, if it's negative, we have to add electrons because it's gained electrons. Again, just be careful. It's really tempting to see that negative sign and subtract, but electrons have a negative charge. So if my net charge is negative, it has more of them, so we have to add. So 24. Xeon. I know xeon's a noble gas. It's in group 8A. Most noble gases do not form compounds, but xeon does. It's actually the only one, and it forms compounds only with fluorine, but it does form a couple different compounds with fluorine. So I know that might look kind of weird. Fluorine, group 7A, there's 5 of them. 7 times 5 is 35. 35 plus 8 is 43. It does have a positive charge, so what do I need to do? Good. Subtract 1. Hopefully that's what you guys said. Again, watch out. It's positive because it's lost an electron. So 42 electrons. So that's our first rule. First rule is we need to figure out the total number of valence electrons in our molecule. So I'm going to go back up to our rules here. Our second rule is we're going to determine the order in which they're bonded, and we're going to connect everything initially with a single bond. So connect with a single bond. Couple rules for doing that. Hydrogen can never, ever, 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 ever go in the middle. Hydrogen, remember, if I look at its electron configuration, right, it only has electrons in the first shell. In the first shell, I only have one subshell, right? There's only one value for L, and then that subshell only has one orientation. And I can only put 2 electrons per orbital because of the Pauli exclusion principle, right? There's only 2 values for m sub s, so because of that, each orbital can only hold 2 electrons. So in the first shell, I can only hold 2 electrons maximum. That's the very maximum in the first shell. A bond is 2 electrons. So if you have one bond, you've like maxed out the number of electrons I can go in that shell. So hydrogen can never go between atoms, right? If I was to do something like this, I now have 4 electrons on hydrogen, and that's not possible, right? This is why it's not possible. So be really careful. Hydrogen, if you draw a Lewis dot structure with hydrogen in the middle, I don't give you a lot of mercy. So hydrogen can never, ever, 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 ever go in the middle, right? Never more than 2 electrons on hydrogen. Never. Never more than 2 electrons, right? That's our maximum. So if I give you like C3H8, bond all the carbons together and then put all the hydrogens around the outside. My next rule is halogens don't generally go in the middle. Sometimes they do, but it's a good place to start if you don't know where to start to not put them in the middle. And then the next one, generally the less electronegative atom goes in the middle. Remember we had that trend on our periodic table where we said, this is a horrible out of scale periodic table, but fluorine is my most electronegative atom. And as we get closer to fluorine, it becomes more electronegative. Remember, hydrogen has about the same electronegativity as phosphorus. So in general, the less electronegative atom is going to go in the center, but do be careful. If hydrogen is your less electronegative atom, it cannot go in the center because hydrogen can never go in the middle. And then the last rule here, it sounds really funny, but it's usually the easiest one. And I don't really know how to say it, so I always word it kind of weird. But if you have one atom of one element and then more than one atom of another element, the one that you have one of usually goes in the middle. So like if I had PCl5, yeah, I guess I can do that. If I had PCl5, I have one phosphorus and more than one chlorine, the one phosphorus is going to go in the middle. That doesn't always work, but again, if you don't really know where to go, that's a good start. So never have hydrogen in the middle. Halogens often don't go in the middle, though sometimes they can, but don't start there unless you only have halogens, right? If I gave you ICl3 or something, then it's all halogens, so one has to. Generally, the less electronegative atom goes in the middle, unless it's hydrogen. Right? Water, oxygen is going to go in the middle, and oxygen is more electronegative than hydrogen, but hydrogen can't go in the middle. If you have one atom of one element and more than one atom of another element, the one that you have one of goes in the middle. So that's going to be step 2. So I'm going to go down and we'll do step 2 to all of these examples. I know in the past you probably have done Lewis structures. I'm going to do a little side note, Kenny, off to the side. And you may have done it the puzzle piece way. So if I was drawing my Lewis dot structure for water, we're going to do it using my rules here. But if you had 130, you might have learned it this way. You might have drawn the individual atoms. So hydrogen, we just said, has 1 electron, so I'm putting 1 dot on them. Oxygen has 6 electrons, so you could put 6 dots on it. Usually you think of it as having 4 sides, and you go around and put 1 on each side. And then you pair them up after that. And then you put the puzzle pieces together. So remember, a bond is 2 electrons. So this is by itself, this is by itself. So we can like connect this over here. And then this is by itself, this is by itself. So we can connect those over there. And then you would end up with 2 lone pairs and 2 single bonds. And that works fine for simpler molecules. For water, you could do it that way. The problem is we're going to do things that are more complicated and bigger in this course, and that doesn't always work. These rules will always work. If you follow these rules in order, and they have to be done in order. If you do them out of order, you're going to get the wrong answer. So if you follow these rules in order, you're going to get the right answer. An example where it wouldn't work, I'm going to go down to my xenon one. If I was to do that, xenon has 8 electrons. And I have 8 dots around it. So where do I put a bond? Like I can't, right? There's no putting puzzle pieces together because it already has 8. So that method isn't going to work for you anymore. So while these rules may seem tedious, rules are nice because all you have to do is follow them, right? If you do step 1 and then step 2 and then step 3, you're going to get the right answer. So we're going to go through our rules. So back to water, sorry, my side note. So hydrogen can't go in the middle, so oxygen has to. So the step I'm on just says to connect them with single bonds. I had said I'm going to use lines for bonds, so this is how I'm going to do it. If you want to use dots, that's fine. I think you'll find that dots get kind of annoying to draw after a while, and lines are just easier. It also looks neater to me. The other thing about water here is that, remember, the Lewis dot structure tells me nothing about the shape of my molecule. It only tells me how those valence electrons are distributed, right? I have 8 valence electrons. How are they distributed in that molecule? It tells me nothing about the shape. So if I wanted to draw it like this, that's equally correct to the way I did it. If you want to do it at an angle, that's equally correct. if you want to do it this way, it doesn't matter. The only thing that matters at this point is that oxygen's in the middle, and then it has a single bond to each of those hydrogens. How you want to do it, again, it doesn't matter. If I want to like squish them super close like this, it's kind of weird. But remember, Lewis only says how are those electrons distributed. So I tend to be symmetrical. I like symmetry. So if I have a left and a right and only two things, I'm going to put one on each side. If you want to do top and bottom or bottom and right, it makes no difference. Just oxygen has to go in the middle because hydrogen can't, and then attach them with single bonds because that's what my rule says. I know I have 8 electrons to account for total. I've only accounted for 4, but we're only on rule 2. So we're just doing rule 2 right now. So we'll sit tight on the rest of them. So phosphorus and then 3 fluorine. Phosphorus is the less electronegative atom. It's not a halogen, and it's the one that I have one of. So I'm going to put it in the middle. And then just like the water, it doesn't really matter where you put the fluorines as long as they're attached to phosphorus. So if I wanted to do this, it would be just as correct as the way that I initially drew it. So phosphorus in the middle, 3 bonds each to a fluorine. I know we have more electrons, but again, we're only on step 2. So hydrogen can't go in the middle, so it must be nitrogen. Carbonate, I have carbon and I have 2 oxygens. Carbon is the less 3 oxygens. Carbon is the less electronegative atom. So carbon's going to go in the middle. And then xenon, I'm going to bond that to 5 fluorines. All right, it's the one that I have one of. And it's not a halogen. So I know I just put 10 electrons around xenon, but remember our first shell, right? So there's only 1 orbital. There's 2 values for m sub s, so I can have 2 electrons per orbital. So 2 electrons max, right? If I'm in my second shell, L is equal to 0 and 1, right? M sub L is 0, M sub L -1, 0, and 1. I now have a total of 4 orbitals, right? One of them is an s orbital, 3 of them are p orbitals, but I have 4 orbitals total times 2 electrons each, right? Still only 2 values for m sub s, which gives me 8 electrons total. Once I get to the third shell, though, right? I have, these are my s's, right? These are my p's. I have d orbitals available. So I can have 2 electrons there. I still have 3 values for m sub L, so I can have 6 electrons there. And then here I have 5 values for m sub L. I can have 2 electrons in each, right? M sub s is still just 2 values. So I can have 10 electrons there. So I can have 18 electrons total, right? I can have more than 8 once I get to the third shell. And if I look at the electron configuration for xenon, my valence shell is shell 5. So I am not limited to 8 electrons, right? In the first shell, I'm limited to 2. In the second shell, I'm limited to 8. Once you get past the second shell, right, once you get to the third shell, I have d orbitals available. So I can have more than 8 electrons. So having 10 electrons around xenon right now, that's perfectly fine, right? Xenon has orbitals that I can put electrons into. Okay, back up. We're still going through, we're still only on rule 2. So rule 3. Rule 3 tells us, we've completed 2, to place lone pairs around all terminal atoms, so those are the ones on the outside, until each has an octet, except for hydrogen, because hydrogen can never have more than 2 electrons. And if it has a 1 bond, it already has 2. Right? Again, hydrogen only has electrons in the first shell. The first shell only has 1 orbital, never more than 2 electrons around hydrogen. So I'm going to put lone pairs around all of my outside atoms except for hydrogen until each has an octet. And then a reminder, we can't go over our total, right? We can't have more electrons than we determined in step 1. So let's go do that. So water, I'm doing my outside atoms again. So it's hydrogen, I can't do anything. Oop, so we're going to skip that one. Sorry about that, guys. PF3, fluorine right now has 2 electrons. Remember that bond is 2 electrons. I want 8. So I'm going to put 3 lone pairs. Remember, you're never going to use lines for lone pairs, and they're called lone pairs because they're always going to be groups of 2. So 2, 4, 6, and then that bond makes 8. So that fluorine that we just put lone pairs on has an octet. I'm going to do this fluorine. It has 2 already from that bond. So this makes 4, 6, and then 8. The bottom fluorine has 2 in that bond. 4, 6, 8. Remember that a single line, right, a single bond is 2 electrons. Ammonium, my terminal atoms are hydrogen, so I'm going to skip it. This one, 2, 4, 6, and the bond is 8. 2, 4, 6, and the bond is 8. 2, 4, 6, and the bond is 8. I know the answers, and that's why I haven't been very good about keeping track, but do remember we can't go over that 24. So do pay attention to that also as you go. Xenon, so fluorine has 2 already from the bond. So I'm going to make sure that each fluorine has 8 total. So I'm going to put 3 lone pairs. Again, don't ever draw lines. And then we want to keep them as pairs. Don't do lone electrons. Those are radicals. You'll do some of those in organic, but for now we want to keep them in pairs. So that is rule 3. Terminal atoms. So let's go back up. It says in step 4, if I have unused electrons, so if I haven't accounted for all of the electrons that we determined in step 1, I'm going to put them on the terminal atom, or sorry, the central atom, central, the one in the middle. And then again in pairs, I'm not going to have lone electrons. So if I look at water here, I have 4 electrons total in what I've drawn already, right? 2 there and 4 there. I need 8. So I do have 4 electrons left over, right? 4 that are unaccounted for. So I am going to go and put those on oxygen as pairs. PF3, phosphorus trifluoride, now that we know how to name stuff. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I need 26. So I have 2 electrons left over, and I'm going to go and put those on the central atom. Try to get all this highlighter off of here and fix my structure. I lost some electrons in the process. Okay. Lone pair on phosphorus. Ammonium, I've already used up 8, right? 2, 4, 6, 8. I need 8, so that one's done. My carbonate ion, I've used up 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I have 24, so that one's done also. Oops. Xeon, I'm not going to use highlighter this time because I don't want to erase it all. But I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. I have 2 electrons left over, and they're going to go on Xeon. The quicker way to actually count that is I know that each one of those fluorines has an octet. And I know I have 1, 2, 3, 4, 5 fluorines. So 8 times 5 is 40. And then I could just say, okay, I have 2 left over. So then those 2 went on Xeon because our rule says to put them on the central atom. So I don't know if you saw them, but they're just squished in here. Okay, 1 rule left. And we don't always need this last rule. So this says if. If an atom that wants an octet still doesn't have an octet, this is where we're going to add double and triple bonds. And it's not really that we're adding them. At this point, we've accounted for all of our electrons. So what we're going to do is we're going to rearrange electrons to make double or triple bonds if we have to. So things that don't want an octet, remember hydrogen can never have more than 2 electrons. Boron is okay with only 6. So if you're doing a Lewis dot structure and you have boron in it and it ends up with 6 electrons instead of 8, that's fine. You can leave it there. And then phosphorus and atoms larger than that can have more than 8 because they have d orbitals available, right? Phosphorus has its outermost electrons in the 3rd shell. In the 3rd shell, we do have d orbitals. So once you get to the 3rd shell, we can have more than 8 electrons. But it wants like a minimum of 8, right? It can have more, but it doesn't want less. So the only one that we have, or the only 2 we should say that are going to have less, hydrogen always can't have more than 2. Boron is okay with 6. Everything else, I want an octet. If it's bigger than phosphorus, I can have more, but the minimum is going to be 8. So I'm just going to look at all my atoms. I'm going to count this. So hydrogen, oxygen has 2, 4, 6, 8. Remember, we're sharing those electrons. So those electrons in the bond belong to oxygen and hydrogen. So oxygen has 8. Each hydrogen has 2, so we're actually done with this structure. So this is my Lewis dot structure or electron dot structure for water. If I look at this one, phosphorus, 2, 4, 6, 8. And then each fluorine, we've already done that one, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So this one is also done. Ammonium. Each hydrogen wants 2 and it has 2. Nitrogen, 2, 4, 6, 8. So this one is also done, with the exception that if it has a charge, we should put it in brackets. And we're going to do formal charge also in this chapter, and I'm going to change this when we do that. But until we do formal charge, if you have a net charge, it's customary to put brackets around it and then put that net charge outside of those brackets. Again, once we do formal charge, we're going to change that, but for now, that's what we're going to do. So carbon in this one only has 6, 2, 4, 6. Carbon wants an octet, right? Carbon's not boron, it's not okay with 6. So it needs to have 8. So what I'm going to do, and it doesn't matter where you take them from, but I'm going to take 2 electrons from one of my oxygens. So I'm going to take those 2, but I could have taken those 2 or this 2. It really doesn't matter. I'm going to take 2 electrons, right? One lone pair from oxygen, and I'm actually going to move them to share them between oxygen and carbon. They'll still belong to oxygen then, so oxygen will still have its 8 electrons, but they'll also belong to carbon. Remember, we're sharing them when they're covalent bonds, so then carbon will also get 8. So I'm going to erase those 2, and then I'm going to move them here. So if I count now, carbon, 2, 4, remember each line is 2, 6, 8. And then if I count for that oxygen that we just did, 2, 4, 6, 8. And then the other 2 oxygens also have 8. So this is going to be my Lewis structure for carbonate ions. And then it does have a net charge, so brackets, and a -2. Xeon, those fluorines we know have 8. Xeon itself has more than 8. So this is done with the exception that it does have a positive charge, so brackets and that positive charge.